All right, so hello everyone. Today we're looking at a volume problem. We have find the volume bounded by z equals 0 and z equals x squared plus y squared over the region R, where R is the set of all points, x minus 2 squared plus x minus 2 squared plus y squared less than or equal to 4. Okay, so if you're looking at this in 3 dimensions, what you have is this like paraboloid that's coming out, and you have the green disk or circle, and you're basically integrating this over, sorry, z equals x squared plus y squared, excuse me, integrating that over that circle, okay? And the idea is that you get some volume out of this, and it would look like, oh, I can't draw that too well, sorry. Yeah, it looks something like that, drawing it. Now, if you were to see it in 3 dimensions, this is an example of that. And yeah, so all the stuff that you see, so z equals x squared plus y squared is that shape. Sorry, I can't point to it, but it's that shape that I drew that looks like the paraboloid. And the volume basically consists of this big chunk that you see whose base is that circle, okay? That's what this kind of refers, that's what that's referring to. So I'll just give you an idea what this actually looks like in 3 dimensions. And by the way, I totally recommend this website where I plotted it. It's called CalcPlot3D. Very useful site to when you're plotting things out in 3 dimensions. All right, so let's move to the actual calculation. So we have a rule that says that if you've got a function, 2-dimensional function, and it's greater than or equal to 0, then its volume over a region is equal to double integral over the region R of the function itself, dA. So we're assuming here the function is it could be actually positive or negative, but I'm just, for the sake of argument, I'm just gonna go with the fact that it's always positive, and then that's what it will apply here. And you would go ahead and try to integrate this now. The region we're integrating is over that circle, so that's what it would look like in 2 dimensions. And as I've done, let me erase this so we can get a fresh start. I'm gonna basically copy down the same thing, but I want to explain what we need to do, and why I was doing what I did down there, the writing. That region we're integrating about, we can integrate it in terms of a rectangular coordinates, but that would be too hard, a little difficult. So let's consider, switching it to polar coordinates. And for me to do that, to see what this looks like in polar coordinates, I need to rewrite this equation in terms of r and theta, okay? So if you FOIL x minus 2 squared out, it would be this. So you get x squared minus 4x plus y squared is 0, or x squared plus y squared equals 4x. Oops, 4x. And now, we have these conversion factors, x equals r cosine theta, and then x squared plus y squared equals r squared. So another way of writing this would be r squared equals 4r cosine theta. Or if we move that 4r cosine theta over to the other side, you would get r times r minus 4 cosine theta. And you get r equals 0, r minus 4 cosine theta equals 0, and r equals 4 cosine theta. Now, this is what I care for. I don't care about r equals 0. That's a single point. So my graph that you see for that disk is represented by a 4 cosine theta. Okay. So when I rewrite these in terms of excuse me, this integral in terms of polar coordinates, for sure I'm going to be using that 4 cosine theta. Now, how would I convert? Well, let's go ahead and let me just stick to what I have here. And I'm going to go ahead and erase this. right here. And yeah, let's go ahead and look at that double integral that we need to compute. And yeah, it's x squared plus y squared dA is what we're integrating. And you're going to go ahead and, first of all, you're going to convert this dA to r, dr, d theta when you're switching this out to polar coordinates. And x squared plus y squared is r squared. So everything that's in the integrand also gets converted. And then we'll figure out the limits, which is usually the hardest part with these problems. Okay. This graph, r equals 4 cosine theta, you can graph that with r going from 0 all the way to pi. Okay. So 0 to pi would, theta, it goes from 0 to pi, excuse me, would graph that whole equation. Okay, I'm not going to get into that, but that's the angle that you would need. However, here's the issue with that, in the sense of, a lot of people will say, you know what, well, you told me that right there, then I'm just going to set up my integral as 0 to pi, 0 to 4 cosine theta. That's not going to work out for you. The main reason here is because when you're doing an integral involving an area here, you need to work with r being positive. R is either always positive or negative in the region of integration. In that region of integration, r equals 4 cosine theta, and picking a value from 0 to pi is both positive and negative, right? Everything from pi over 2 to pi specifically makes r negative. So that is why the setup won't work. However, I'm going to use the fact, something I just said right now, that the limits only work when the function is either always positive or negative. So imagine this is theta equals 0 right here, this angle, and that's theta equals pi over 2 right there. Your graph would always be positive there. So my limits for integration here would be 0 to pi over 2, and then 0 to 4 cosine theta. Yeah, because if you look at the values of r 4 cosine theta is always positive pretty much up to pi over 2. But you might say, yeah, but that only covers from what I just drew here. Yeah, from 0 to pi over 2, that describes the stuff in red. I need the stuff on the bottom. So what we do is this: we're going to multiply this by 2. We use a lot of symmetry in this class in general when you're integrating, but especially with polar coordinates. Yeah, because what you're doing down here is you're kind of looking at the same values pretty much. Okay, that's why we're multiplying by 2. And yeah, that's how that would work out here. Okay, so that would be my integration. You go ahead and integrate that, and that would do it for this problem. So once again, we went ahead and tried to find this volume of this region. Go back to the I gave you a little sketch there, not great, so we went to that 3D picture. And remember, Calcplot 3D, awesome site. And just by the way, just Google that, just Calcplot 3D. It's not like calcplot3d.com or anything, just Google it. And as I said, the way we figure out a volume for a function that's greater than or equal to 0 over r, and that's very important. The function has to be positive over the region r. We can use that. And the issue was, well, if I integrated this over the region that was given here, that circle, in rectangular coordinates, that would have been pretty hard. So we converted to polar. X squared plus y squared became r squared. dA is this differential element that became r dr d theta. And we got our limits of integration from the graph. And we needed to use a fact from calc, primarily calc 2 here, that that you would have to put a 2 in front of that integral, because that function becomes positive to negative from 0 to pi. Okay, so and we can't have that when we're writing out an area. So we did what we did here for that reason. Okay, all right, well, thank you for your time, and I hope this helps.